Hi, welcome back, folks. Ready for more word problems? So I've got another example for you. So consider an open top box with dimensions 24 inches by 24 inches. And the question is, what should be cut out of the corners to make the largest volume of box possible? Now I want you to picture what's happening here. So, and a drawing came with this problem when I first found it, although it's something that you could just draw yourself. So we've got this flat piece of cardboard, and we're going to cut the corners out, and then you can, a perforation would go here, 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 and here. So this would fold up, no top, okay, just an open box. And so they're asking us, how big of a corner should we cut out of here so we have the maximum possible volume? So what do we know? We know that the distance all the way across here is 24 inches. Okay, so we have 24. I can't seem to write. That's 24 inches. Now, how much do we cut out? Well, that's what's in question, right? And we're cutting out squares. So if this is x, then this is x as well. Okay, so x here, you could call that x, and call that x, and call that x, and call that x. So we're trying to come up with two equations, right? You have your constraint equation, which is your fixed values that you have going on, and your maximize, minimize equation. And we're of course trying to maximize. And we're trying to maximize volume. So again, that would be your max-min equation, or you could call it your primary equation. So I have volume equals. Now we know the volume just of any rectangular three-dimensional figure is length times width times height. Okay? Now, for our particular picture, let's think about what we have going on. Our length, right? So you could say this distance down here is 24, but now when you calculate the volume, not including that value and that value. So that's actually in between there. This distance from here to here is 24 minus 2 x's. So our length is 24 minus 2x. Okay. Our width, so go in this direction because this is square, is also 24 minus 2x. Now here's the real question. How high is the box? Well, remember, this is perforated right here, picture that this thing is going to fold up. That means it's x tall. Now, you know how we talked about you need two equations, a primary equation and a secondary equation? But in this particular case, look, the equation that you're trying to maximize is got only one variable in it. You're not talking about two different dimensions. You just want to cut out the same square out of each corner. So we don't have to have a secondary equation in this case. What I do need to do, though, is multiply all this out. Unless you would like to use the product rule for 3 factors, I think it's easier just to multiply it out, folks. So let's do it. Volume equals. So here I go. 24 times 24, you know the drill, right? It's going to be 576. 24 times negative 2x is negative 48x. Negative 2x times 24 is going to be another negative 48x. And negative 2x times negative 2x is plus 4x squared. Now, two things. I need to add like terms, those two negative 48's in the middle. And I need to distribute that x inside. So to save space, I am going to go ahead and do both of those things. How about this? How about I go ahead and write it in descending order too? Notice that's my biggest exponent. So 4x squared times x is 4x to the third. X right here times these two guys, they had to be negative 96x. Times x will be negative 96x squared. And then x times this 576 is going to be plus 576x. Now make sure you feel good about that. I don't want to spend too much time on that. That is our maximize, minimize equation. We call it our primary equation. Now what do I need to do with that thing? Well, I need to think about the domain. Y'all's a polynomial, right? So the domain is all real numbers. Now for our particular situation, our x value it can't be less than, it can't be 0, right? I mean, you have to have a box. Okay, so the lowest, I guess, x would be 0. What's the biggest x could be? Well, it would make a whole lot of sense, but if x was 12, it would take you right to the center, right? And then you would fold it up. You still wouldn't have any volume, but x has to range between 0 and 12 or it won't work out. So again, that's what we mean about finding, the domain of the function to meet our particular requirements. Now, to find the maximum, we need to take the derivative. So v primed is equal to 3 times 4 is 12x squared. And then 2 times negative 96 is going to be negative 192x. And then the derivative of 576x is going to be plus 576. So this is my derivative. Now what am I supposed to do with the derivative? I'm supposed to find the critical numbers, right? And to do that, I need to set the derivative equal to 0. So I've got to solve that equation. Now, if they factored, that would be just really awesome. We could go ahead and go right to the quadratic formula if you want to. Now, there's something you may not notice, but 12 factors into or divides evenly into every one of those coefficients. So 12 comes out. It's going to be x squared minus, now 192 divided by 12. Stand by, 16x, and then 576, also divided by 12, is plus 48. So the real question is, can we find values that multiply to be 48 and add to be negative 16? The good news is we can, okay? That's going to be 12 and 4. So you got x minus 12 times x minus 4. So when we solve equal to 0, I get a critical number of x equals 12 and a critical number of x equals 4. Now remember, what we're supposed to do is take our critical numbers and our endpoints and plug that into the original function. What is the original function, you say? This guy right up here. Okay, so when I plug those values in, right, I have 4 times, now my endpoint, I got a 0. Y'all, if you plug 0 into that, you just get 0. And 0 would minimize the volume. That gives you 0. So that's an absolute minimum. Not going to even write it down. It's absolute minimum. When I plug in 4, so 4 to the third minus 96 times 4 squared plus 576 times 4, what do we get? I think it's 1024. Notice I said I think. Inches to the third, right? Because that's volume. Okay. Now, what's going to happen if I plug in 12? Now, picture what's happening. If x is 12 long, that means the fold is right there in the middle. And if I fold right there in the middle, I have 0 volume. So 4 times 12 to the third minus 96 times 12 squared plus 576 times 12 better equal to 0. I'm not even going to check it because there should be no volume there. You check it. Make sure it's really 0. You let me know if it's not. But this would be the maximum volume. Now, it's asking, notice, go back and read the question when you finish. It said, what should be cut out of the corners to make the largest volume of box possible? And that would be our X answer. So we need 4 centimeters cut out of the corners. And that answers the question. Neat problem, don't you think? All right, we got a rectangle is to be inscribed in a right triangle having sides of length 6. All right, got another problem, question C. A rectangle is to be inscribed in a right triangle having sides of length 6 inches, 8 inches, and 10 inches. It says find the dimensions of the rectangle with greatest area, assuming that the rectangle is positioned in the figure. You almost have to be given a figure here to really follow what's going on. You see the 6 inches happens to be across the bottom. The 8 inches is like the height over here, and then 10 inches is the hypotenuse in this right triangle. Now it says find the dimensions with the greatest area, assuming the rectangle is positioned in the figure. So here's what we're thinking. You know, this is what I have in yellow here is just an example rectangle. Can you imagine that if you slid this point right here down, it would make a longer rectangle? So the length would be longer than this rectangle, but the height would be shorter. On the other hand, if you slid that corner up, you would have a taller rectangle, but not as wide. So we're trying to figure out where to draw the rectangle in so we have the most area we could possibly have. Okay? Now this problem might not be very intuitive, and I can tell you what would help the most is behind our picture here, I'm going to draw an XY axis. That's really going to be the key to this problem. Sorry, y'all, struggling with my screen moving around. I think I've got it lined back up. So here's our XY axis. That's the X axis. That's the Y axis. It's kind of behind scenes back there. But what it's going to do is it's going to make it a lot easier to talk about this problem that we got going on. So if you think about it in terms of X, we could just move this vertical left boundary to the left a little bit, and that would automatically change the height as well, right? Because it's really just moving this corner, just moving this one thing. So here's what I want to do. I want to label the distance from the center to that first vertical mark right there as X. Okay? And this distance would be Y, right? When you measure X, you got to go from the origin for it to be accurate. And when you measure Y, you got to go from, again, the origin to be accurate. So this true distance of this rectangle is Y. So if I scooted this over, Y would be shorter. If I scooted this way, Y would be taller, right? Now, so the height of our rectangle, or you could call it the width of our rectangle, is Y. But now the length of our rectangle across the bottom is not X, because that's where the rectangle is not. You agree? So how could we write the width of our rectangle? Remember, this whole distance all the way across is 6. So if we write that as 6 minus X, that would give us the width. So this distance down here in red across the bottom is 6 minus X, whereas this distance this way is Y. Does that make sense? Okay. Now I want to talk about our equations, right? I think you clearly see we're talking about maximizing the area, right? Find the dimensions of the rectangle with the greatest area. So we're maximizing area. Well, we know the area of a rectangle. Area is equal to length times width. Well, per our picture, area is equal to, again, the length we decided was 6 minus X. And the width, or the height, if you want to call it that, is Y. So that's where we are right now. Area equals 6 minus X times Y. But we don't have a constraint equation. We need to focus on our constraint equation. What is constraining this? What's applying limits to this situation that we have going on over here? Like if I move this over here, how does that relate to Y? Remember, if I move my length, if I make my length shorter, it makes my Y taller. And what is it that's constraining that? Well, it's this line right here. Well, tell me about this line right here. What's going on with that line? Well, first of all, it's a straight line. Can we write the equation of that line so we know what's going on with our XY value? Because our point, XY, has to fit on this line. Well, can we write that as an equation? What about Y equals mx plus b? That's how you write the equation of a straight line, right? Well, how can we do that? Well, tell me about this point up here. We know a point on the line. We know another point on the line, so that means we can find the slope. We know the y-intercept, don't we? Yep, so we can write the equation of this line. Let's find the slope. M is equal to y2 minus y1 over x2 minus x1. Again, I need a point. Y'all tell me what's this point right here. Well, the x is 6 inches, because they told us our triangle was 6 inches across and 8 inches high, so that point up there is 6, 8. So when I find the slope, y2 minus y1 over x2 minus x1, my y2 is 8. My y1, what is my y1? 0, right? My x2 is 6. What's my x1? 0. So my slope is 8 over 6, which is 4/3. All right, so I plug 4/3 in for my slope. I have y equals 4/3 x. What's my y-intercept? That's that guy down there, plus 0. So my constraint equation is the straight line 4/3 x plus 0. And I'm not going to put the plus 0. All right, now what do? Once you have your constraint equation, which is here, you plug it into your max-min equation, which we're maximizing. So our constraint is applied. So I'm going to plug that y equals 4/3 x right there. That's going to give me area now is equal to 6 minus x. Remember, that was your length, times your height is y, but now we're going to write it as 4/3 x. I distribute that 4/3 inside. So I have 6 times 4/3, which we know is 24/3, which is 8x minus 4/3 x squared. What do? I take the derivative, because that's what we do in this whole chapter, right? The derivative of 8x is 8. The derivative of 4/3 x squared is minus 8/3 x. Now what do? I find critical numbers. How do you find critical numbers? You set the derivative equal to 0. Okay, and solve. So I'm going to add the 8/3 over. I'm going to divide both sides by 8/3, which is the same as multiplying by 3/8. So I'm going to multiply by 3/8 over here, multiply by 3/8 over here. What do I find out? Well, I find out that x is equal to 3. So x equals 3 is a critical number. What else? Where is that function undefined? I don't know where. It's a polynomial, right? So the only critical number I have is x is equal to 3. Now, we talk about the constraint equation, but we talk about what are reasonable limitations for our x values. And this is a function of x. Well, the smallest x would be 0, right? Okay. What is the biggest x could be? 6, because we're talking about across the bottom here. So if x scooted on over there, you wouldn't actually have any volume. If x scooted on back here, you actually wouldn't have any volume either. Okay, the 0 to 6. Now, we're supposed to check every endpoint and any critical numbers that come out in between. But y'all, again, if x is a distance of 0, that means there's no height to our rectangle. If x is a distance of 6, that means it moves all the way over here and there's no width to our rectangle. So both of those are going to have a volume of 0. So let's just plug in 3 and find out about our rectangle. So where am I plugging it in? I'm plugging it into my area equation right here. So we have area equals 8 times 3 minus 4/3 times 3 squared. So it's going to be 24 minus, now one of 3's cancels with one of those, minus 12. So basically our area is 12. We're talking inches, so that is inches squared. Now, what did it ask? It said find the dimensions of the rectangle. Well, we got the x value is 3. But now that's not the dimensions of the rectangle, right? Our length, remember, was 6 minus x, okay? So that's going to be 6 minus 3, which is 3 inches for length. Our width, or our height, was y. How do you find y? Well, back over here, or here, y is equal to 4/3 x. So it's going to be 4/3 times, our x was 3, which is 4 inches. So our triangle is 3 inches by 4 inches, again with an area of 12 inches squared. Interesting problem. Right now I know that wouldn't have been all that easy to follow had we not put this on an XY axis. That really was the key to solving this problem. Okay, here we go. A wire of length 12 inches. So picture a 12-inch wire you got in your hand, right? It can be bent into a circle. It can be bent into a square, or it can be bent into a circle and a square if you cut it into 2 pieces. So you can picture doing that, right? So you've got a real-world picture of what's going on here. It says how much wire should be used for the circle to maximize the area. Okay? Now, it's just asking about the circle. That doesn't mean doing a circle only. What we're talking about, we're trying to maximize the area. Do we make just a circle? Do we make just a square? Or do we make a circle and a square that could be of varying lengths? Okay? Now, it doesn't say cut in half either. It says cut into 2 pieces. So you're trying to maximize the area. So let me go ahead and set you up here because you're thinking about having to cut this wire. So you've got this wire. How long is it? The whole thing is 12 inches. Okay. So you're imagining that possibly we're going to cut this wire, not in half. So you have a piece. I'm just going to do a pretend mark. So one piece is called X. And I need to, instead of calling that Y, we already have a constraint on this. We can call that 12 minus X, kind of like in the triangle problem we just did. Do you agree with that? So if this is 4 inches, then that's 8 inches. Or if this is 1 inch, then that's 11 inches. So that's the way you can name it without actually picking a value to cut for X. So this is how our wire works. Now let's talk about the perimeter, okay? Because the perimeter matters because that's what our shape is going to be. So when you talk about the square, okay, then we can use, let's let that be over here. Better yet, let's do it this way. Let's let the circle exist here and the square exist over here, right? So for the circle, okay, we're going to use this X piece to wrap around my circle. The question is, how long is it going to be? Right? So you have X is equal. Now, how long is a circle? Well, it's 2 pi r, right? So however long the radius is 2 pi r. That's the length. So we know this piece is going to be 2 pi r long. Okay? And when we think about the square, you think about a square. Mine looks like a rectangle. Let's pretend it's a square. That means that all 4 sides are the same. I'm just going to call that L. Okay, for length, you could call it S for side. So you have 4 L's is going to equal 12 minus X, because that's all we have to make our square is 12 minus X. So X, the X piece makes the circle, which is 2 pi r. The 12 minus X piece makes the square, which there are 4 lengths. So that's called L. Each side is called L. So that's a way to get started. Now let's continue and think about, just our thinking process. So right now, that's some constraint equation. We've got this wire. We've split up. One part of it we call X. The other part of it we call 12 minus X. No matter what, that adds to 12 inches long. Again, a circle is 2 pi r, so the radius matters on the circle, whereas the square is 4 times your length, and so we said 4L was equal to this piece over here. So kind of like dealing with your constraint. Now let's talk about area. All right, so once again I'm moving my screen around. There's area. Now the area of our circle, you know how to find the area of a circle, right? Area of a circle is, drum roll, right? Pi r squared. Right? Well, what about the area of a square? Now, at least use L, okay, because we've already used L in our picture. Well, the area of the square is L times L, or L squared. You good with that? Now, what are we doing with our areas? Well, we're adding them together. We're trying to find the maximum area. So our total area, I'm just going to call it A, also, is going to be pi r squared plus L squared. So far, so good. So the area of the circle plus the area of the square, we've got it. Now, that doesn't take into account our information we found before. So now we're going to use these constraints, because that's what that really is, our constraints. Our real constraint is our wire is only 12 inches long. That's our true constraint. But mathematically, that's the situation, is that the circle is going to be made out of this piece we called X, and the square is going to be made out of this piece called 12 minus X. Now, if I could get rid of this R and get rid of this L and have all the same variable, I'd be doing great. Okay, well, L is not written in terms of R, and R is not written in terms of L, but you know what? R can be written in terms of X over here. So what I'm going to do right up here, and you're going to do it neater somewhere else, I'm sure, is I'm going to solve this thing for R. So I'm going to divide both of these by 2 pi. And now I've got that R is equal to X over 2 pi. And this guy right here, I'm going to solve it for L, okay, by dividing both sides by 4. So divide by 4, divide by 4, divide by 4, and I get the fact that L is equal to 3 minus X over 4. What am I going to do with that? I'm going to substitute that straight into my maximize-minimize equation. So area now is equal to pi, again R, he's right here, so X over 2 pi, but that's supposed to be squared because it's R squared, plus L squared. We know L is 3 minus X over 4 all squared. So there we go. We have now an equation with nothing but X's in our problem. You know what that means? That means we can take the derivative. Now, as you can see, there's a lot of algebra that's got to happen here. We want to simplify this as much as possible. So a lot of the work on this problem, once you get past this awesome setup, is simplifying the algebra before we even take the derivative. Okay, so let's do that. I want to square this X over 2 pi squared. So at the top of the page, here I go, I've got area is equal to, there's still a pi in front, correct? And then when I square, I have X squared over 4 pi squared. And then this pi cancels with one of those. So that simplifies to X squared over 4 pi squared for now. Now I'm not finished. I still got this plus over here. Now that whole thing is squared. So I'm going to write it out. 3 minus X over 4 times 3 minus X over 4, and FOIL that out. There's other ways you could handle it as well, but this works for me. All right, so 3 times 3 is 9. 3 times X over 4 is minus 3/4 X. Negative X over 4 times 3 is another minus 3/4 X. And then negative X over 4 times negative X over 4 is plus X squared over 16. Now, got some like terms here. So I have A is equal to, how about we write this as 1 over 4 pi squared times X squared. Look, there's another X squared over here, so plus X squared over 16. And then here, I'm going to write these two guys is minus 6/4 X, combine like terms, and then plus 9. Yeah, I know that feels weird, right? It's okay. Listen, these are like terms, but writing these fractions with a common denominator might not be worth it. So here's what I'm going to do. I'm just going to factor the X squared out. So the coefficient for this is ugly, but that's okay. Yeah, that's just a constant, so don't let it bother you. That 1 over 4 pi, I almost lost the square though. Oh, or is it there? Ooh, it's not there, y'all. Almost messed up. Look. Look, look, look. That is not there. Okay, so that's 1 over 4 pi because that one of those squares cancel with that one. Plus the 1 over 16 times the common X squared minus 6/4. I'm going to write as 3/2 X plus 9. It never feels right when you have all those ugly looking values, but I do believe we're doing it right. Now let's take the derivative. So A primed. Now y'all, this is just a polynomial. It's weird looking with its coefficients, but it's just a polynomial. And so the derivative using the power rule, I'm going to move the 2 in front of that strange looking coefficient. And so now it's x to the first minus 3/2, and the derivative of 9 is 0. Now what am I supposed to do with that? I'm supposed to set it equal to 0. So I have 0 equals all of that. Okay. Now remember, I'm solving for x. Where in the world is x? It's easy to get lost. It's right there. Okay. So what I have to do is I have to get the x by itself, right? So what I'm going to do is I'm going to add 3 halves over. And you know what? I'm going to erase the 0 equals. So just pretend like all that's equal to 0. Let me put it down there. Alright, so I'm going to add the 3 halves over. So I have 3 halves is equal to 2 times this ugly coefficient, which is 4 pi plus 1 over 16 x. I'm trying to get the x by itself, so I'm going to divide by 2. That gives me 3/4 is equal to 1 over 4 pi plus 1 over 16x. Now what do? I divide by that ugly coefficient. So my x is equal to 3/4 divided by 1 over 4 pi plus 1 over 16. And then when you get an answer like that, you think, surely I'm doing something wrong. But I don't think we are. So what I do want to do, I mean, you could try to simplify that more, but yeah, let's just type it in. Let's get a decimal version of this and see where that takes us, okay? So I got 5.2788. So it's not pretty, but that is our critical number. See, I'm out of the page. I can't finish. Not really. Let's go to another page. So now I've moved the important stuff to this page. Remember, we had a formula for area. That's it, not multiplied out. And we have a critical number. Now we're supposed to take the critical number and plug it in, but remember we also have some like endpoints that are going on in our situation. Remember, there's one possibility of the circle only. And remember, there's one possibility of the square only. And then we have the critical number we could plug in. So these are like 3 different situations. If we did the circle only, wouldn't really be an issue. More like, remember, the circle only is just the length of our wire is equal to 2 pi r, which would mean our radius, if I solve for r, is 12 over 2 pi, which is really 6 over pi. Now when I'm going to do that, I've got to find an area. So remember, area is equal to pi r squared. So that's pi times r is 6 over pi squared. Okay, so when I simplify that, 6 squared is 36, and this is pi squared, but it cancels with one of those pi's. Now how big is 36 over pi? 11.459. So that's one situation. And then what we do for the square only, let's think about that. So 12 is equal to 4L. So how big is every side? Well, it's 3 inches. And then the area of a square is 3 times 3, so that would be 9 inches squared. This would also be inches squared, okay? Well, this one's bigger than this one. And then for the critical number, you would take that 5.2788 and plug it in. So this will be pi times, back of this top equation, 5.2788 over 2 pi squared plus 12 minus 5.2788 over 4. All of that is squared. To save a minute, I'll tell you that I got an answer of 5.0409 inches squared. I kind of just cheated off a worksheet I'd already done earlier. Hey, what's bigger? What's the biggest answer? Oh, the circle only. Does that make pretty good sense? That the circle only would give you the most volume? It kind of makes sense in my mind. All right. I'm going to come back for a third video for more problems. Have a good one. Actually, I'd like to make an additional comment on this problem. If you'll notice, when I did the circle only, I thought about it like if we were only doing a circle, it would take 12 inches of wire. But you can just use this formula. I don't want you to think that, what about that formula? What happened to that formula? You can use that formula. If you'll recall, if I flip back a page, remember the circle only would mean all x goes to the circle. So that would be the same thing as saying just let x equal 12 and plug it into the area. And see if you don't get 11.459. I'm not going to check it right now. You should. Okay, without a doubt you should. The way I calculated it is just thinking through it, but really you could use the formula. On the other hand, for the square only, okay, if you think about our picture again, the square only would mean x is equal to 0. No room for the circle, so you could use that formula to do square only with x is equal to 0. And again, you should get 9 inches squared. And then finally, our critical number was that awful 5.0409 rounded that I plugged into the function. And we found out that, not 5.0409, I'm sorry, 5.2788 that you plug into the function, and you get a similar answer as the critical number. And again, the largest was the circle. Alright, now I'm for real finished. Come back for video 3 where I do 2 more problems.